Good evening, everyone. Welcome to uh, problem solving sessions for week 9. Today, I'll be discussing linear models and a little bit on linear regression and how to solve it with R. And yeah, that is all I'm going to cover in today's lecture. So, let's start. I'm Shreya, one of the TAs for this course. Okay, so in the last classes, we learned a lot about sampling and also about methods of estimating the mean, how to get the population parameter, how to get estimates of mean, how to get estimates of variance of sample mean, and then how to get an estimate of the variance of sample means using simple random sampling, using stratified sampling. We learned about uh, when to use which method of sampling which is most appropriate in certain cases. And then also we touched upon what to do, or yeah, we learned about something called bootstrapping, which is particularly useful when you have a small sample size and when you are not in a position to apply the nice properties that you can when your sample is large. And also you have to estimate some measure of some central value which is different from mean. It could be median, it could be coefficient of variation, it could be something else. Particularly, we learned about this thing in the context that this is helpful when the estimates do not have, like, the analytical form of the variance of the estimates are not particularly very good looking, or they are not readily solvable analytically. So in that case, in those cases, what do? We have a population, we draw samples from that, and then from that original sample we keep on resampling with the hope that that sample is actually representative of the population, and by resampling we are able to obtain estimates of the quantity that we want. Could be mean, could be coefficient of variation, and we can also empirically or yeah, we can also in some way have the estimates of the variances. So this is all what we learned during the past 8 weeks. In this week we are going to learn about, okay, we have, one second, sorry. Yep. So here so where was I? Yes, so in this today's session we'll be learning about linear models. Okay, which is an important part in the sense that, let's say, with this linear models we will be able to approximate some, I'll put between, let's say, two variables x and y. Okay, so I mean to say we with the help of linear models we would be able to approximate relationship between two random variables x and y. Okay, so if I have to give an example, so let me start with this example. So let's say my y variable, so let's say I am a farmer. Okay, and I am interested in looking at yield of a crop. Okay, now this yield is affected by several factors. Okay, one could be it is directly affected by the number of the amount of rainfall. It is affected by, let's say, quality of seed. It is affected, let's say, whether it is genetically modified or not. It is affected by soil. It is affected by temperature. Okay, so with the help of linear and also there could be some other sources which are affecting, but we are not aware of those sources. Okay, so if I want to model the relationship between all these factors and my study variable of interest, I can go ahead and use a linear model. Okay, so my goal is to find how they are affecting, whether they are affecting, and if they are affecting, how they are affecting all these other factors. Okay, so these ones which I underline are like my the green ones are like sources of, I could say, variation. Okay, depending on these things it is expected, so these are like expected sources of variation. Okay, now just to be extremely careful, all of these terms that I'm using are right now in this context, these are like generic terms, but if we go deeper, these we just can't use expected sources of variation to describe these things, but essentially to convey the idea, I am just calling these factors which seemingly influence y as my expected sources of variation. Okay, all right, so Now that I know that, or I don't know, I am assuming that there could be a relationship between these factors and my variable of interest, that is soil. The another example that I can think of currently is that, let's say um, I am uh, a real estate manager of some sort or something, and my y of interest is, let's say, price of an apartment. Okay, so again, this one can be affected by several factors. So I know the price of an apartment will be definitely dependent on floor area, how much big the flat is. It will be dependent on whether it is, a standalone or in some complex. Okay, it would be dependent on the region where it is, whether it's in an urban area or whether it's in a rural area. It could also depend on something like number of amenities. Okay, it would also depend on how old the building is. Okay, these are something that I can think of. It can also depend on whether we have marketplace nearby. It can also depend on transportation or something like that, like whether it's in a area where you find public transport or not. So these are some of the variables that I can think of. Apart from this, even if all of this is same, even then we find certain differences in price of an apartment. That is uh, due to some other factor that we don't know. Okay, we can call, we can assign those differences in prices to some other unknown factor. Okay, so here again, these are like my potential variables which can influence y. Okay, so if I am facing such situations where I have one or more variables which influence a particular variable of my choice, of interest, then I am probably looking at I mean, if I want to model the relationship, uh, the first step would be to go ahead and uh, build a linear model. Okay, now what does these two situations, if I want to mathematically quantify these two diagrams into a certain mathematical formula which depicts the relationship, so if I want to write this, so if I want to write a mathematical formula depicting the relationship Then very crudely, if I call them as my x's, if I call my influencing factors as x's, then I can say that my variable y is actually a function of the x's. Okay, now this f is actually unknown. We don't know what the functional form of this is. Okay, so if f is known, or if we can somehow guess what f could be, then we can say we are able to quantify the relationship between x's and the y variable. Okay, so whenever I am depicting the relationship in this manner, such that we have some variables who have some influence on my variable of interest via some mathematical form, we are trying to model and find out what the mathematical form is. So in such situations, my y would be called a dependent variable, and the x's are the independent variables. Okay, these terms are self-explanatory. Why is dependent? Because values of y depends on the values of x through this unknown formula f. So if we are able to get f, we know how exactly y is dependent on x's. Okay, so the task at hand is to determine f or find a suitable relationship between y and x's. So what do I mean by suitable? I mean to say that which aligns with the data, observed data. Okay, so based on the observed data, we are going to devise or guess what the form of f is, in such a way that we are confident that okay, this whatever observed data points I have, they are actually generated in that process. Okay, so here we are sort of trying to derive the process with the help of data. And what are we using to do that? We are using the mathematical relationships between the dependent and independent variables. Okay, so by a model, I mean that I am in some way characterizing the relationship. So modeling means characterizing the relationship between y and x's. Okay, and in such a way such that the salient features of the underlying process is well incorporated. Okay, in other words, it means to say that I am trying to characterize this relationship on the basis of the observed data, and I should be convinced that yes, that relationship actually uh, holds true. True in the sense that that relationship actually exists, and that is what is giving me the observed data. Okay, so given all of these, we would like to have a model like this: f x1 x2 xk, something like this. Okay, now if let's say y is completely determined by some analytical form of fx. Okay, so what I mean to say is that let's say uh, I have such a relationship that whenever I know x1 x2 xk, I have y, and if x1 x2 xk remains same, I obtain the same y. But so if this is the case, that let's take that apartment example. So if apartment 1 costs something around say 80 lakhs, and it has a square foot area, let's say 1000 square feet, and it is like close to, I mean, it has all the amenities. Okay, so all amenities that one can think of. It is located, it has access to transportation, so everything is there. Let us only focus on these three variables. So access to public transport is good. Okay, and I also have another apartment y2, which is also 80 lakhs, same x1 x2 x3. Okay, now if I have a situation such that if all x1 x2 x3 remain same, I would land up with a same apartment price, then I would have something like this, which is actually a mathematical model, which means x is same, y will also be same always, without fail. Okay, so this is a mathematical model, like the equations that we use in physics. Those are like universal mathematical models, PV equal to nRT or something like this. Okay, so these things will definitely hold true, or Fahrenheit to Celsius conversion, let's say. Okay, so these models are actually mathematical models. But in real life, mostly we have something like this: f equal to x1 to xk plus epsilon. Now this is what we were talking about in terms of unknown. Okay, so given everything is fixed, I have all the amenities in the world, I have the exact floor area and everything, even then it is expected, I mean, in real world what happens is that I would have a different y. So that is because of this unknown random error factor. Okay, so this sort of a model where we have some part of the variable where the variation in my variable of interest can be attributed to some unknown random quantity. This is actually a statistical model. So now that we know what a statistical model is, let us now find out how we can differentiate between a linear and a nonlinear model. So henceforth we are going to be talking about statistical models. Okay, now we have learned about modeling and the concepts behind modeling, what we mean by it and what we are essentially trying to achieve. Now then comes the keyword linear model. Now this one, it may sound that linear model means we are going to fit a line, but we should be extremely careful in thinking in this manner, because linear model doesn't always imply that there would be a line joining y and x. What linear tells me is linear in terms of parameters. Okay, linear model is, it means that it is linear in terms of parameters. Now what are parameters? Parameters are usually denoted by betas, beta naught, beta 1, beta 2, beta p, something like this. Okay, so these are parameters are actually unknown and they help model y. How? So if I write y equal to, let's say, beta naught plus beta 1 x1 plus beta 2 x2 plus beta 8 x8 plus epsilon, then these betas are actually the unknown parameters which are helping to find a relationship between the dependent variable y and the independent variables x's. Okay, now how do we say if a model is linear in parameters or not? So if y or expectation of y, if we differentiate, let's say y or expectation of y, then we should have so this one, whatever expression we have, this should be free of beta naught. Whatever expression here we have should be free of beta 1. Okay, so essentially it boils down to this fact that this one, the power of this should actually be 1. Okay, so this is actually a linear regression. Okay, and we are considering partial derivatives. So whenever we do a partial derivative, we assume that all unknown parameters are constant or known, right? So this is actually an example of a linear regression. So again, if I want to fit something like this, beta 1 equal to beta 1 x1 square plus beta 2 x2 x3 plus beta 3 x root x. So even this one is a linear model. Why? Because if I do del y del beta naught, or let's say del of expectation y, so this one I'll only have 1. If I do del beta 1 expectation of y, then I'll have x1 square. So this is free of beta 1, this is free of beta naught. Okay, so this also is actually a linear model. But see here, x is having, x1 is in quadratic terms. Here we have another x which is like root x. Okay, so I could have all sorts of x's, but my betas should be linear, in the sense that they should have power 1, and whenever we differentiate partially with respect to however many number of parameters we have, all of these partial derivatives should be independent of the beta that we are obtaining the derivative of. Okay, so this is how you so this is how you would call a linear model a linear model. So just to give a counter example, if I have something like this, y equal to beta naught plus beta 1 square x1 plus beta 2 square x2, something like this, then if I do del beta 1 expectation of y, let's say this is my expectation of y, Then what do we have? We have 2 beta 1 x1, which is dependent on beta 1. So this is not linear. Alright. So now hopefully if you get questions where you are asked to find out whether a linear model is actually linear or not, you know you would have to look at the parameters, get the partial derivatives, and if we don't have those things, then if the partial derivative is independent of my parameter of interest, then I have a then I have a linear model. Okay. Now after determining whether we do have a linear or non-linear model, we should be wanting to fit those linear model. Now what do I mean by fitting? So let's say I have my y equal to beta naught plus beta 1 x1 plus some beta p xp or beta k xk plus epsilon. Now beta naught, beta 1, beta k is, they are unknown. By fitting, what I want to say is that I want to get beta naught hat, beta 1 hat, beta k hat. That is, I want to get estimates of parameters. And how am I going to get it? By utilizing the observed data. Okay, so this is what fitting models is conceptually all about. That is, I have a linear model. I want to quantify the relationship. If I assume that it is a linear model, that is linear in terms of the parameters, then using the data, I want to infer what the values of these unknown parameters could be. Okay, so the main thing here is using data. So this is the most important thing, using the data to get estimates of these unknown parameters. Now these parameters are also called regression coefficients. Okay, right. So now we are going to use the data and follow some particular steps and get these beta naught hat, beta 1 hat to beta k hat. Alright. Fine. So now that we want to infer the relationships, what are the major steps in regression analysis? So majorly we need to formulate the problem or a statement which we are trying to address. Okay, so we need to at first formulate the problem statement. What is it that we are trying to do? Okay, the next thing, so in the farmer example, we were trying to see the relationship between we were trying to find out what affects or influences the production of a crop. In the second example, we were trying to assess what could affect the price of an apartment. Okay, so in both the cases, if you see, we took some relevant variables. So this is also a very important step, that consideration of relevant variables. Okay, now I should tell you that oftentimes the relevant variables may also depend on the domain of study. Okay, so going further, we are going to test if these relevant variables are statistically relevant or not. But even then, what I mean to say is that process of testing statistical relevance should not deter someone from selecting relevant. What I'm trying to say is that testing for those statistical relevance is a much later thing. Initially, we should take all the variables that we feel are relevant to the problem. Okay, and also it's not as straightforward as it sounds, because if we are considering surveys for data collection, then if we increase the number of variables, we are going to there could be an increased cost associated with it. So keeping everything in mind, with whatever resources that we have at hand, we should choose the relevant variables. That is all I am trying to say. And whatever we are not able to explicitly state, that part we are going to assign to the epsilon or the random error term. Okay, now once we have considered the relevant variables, as I was saying, we need to collect data on the relevant variables. So for example, in this let's say in this crop example, I have access to all these information, whether how much of rainfall the soil has received, what is the alkaline content of the soil, or acidic content of the soil, how much is the temperature, what is the quality of seed. Let me assume that I have all the information. But this one, whether it is genetically modified or non-genetically modified, this information, let's say it is not available directly, but we'll have to do some sort of testing to actually find out whether this is a GMO or a non-GMO crop, and it's not stated in the seed bag, let's say. So if determination of GMO versus non-GMO is a very costly process, if I don't know whether it is costly or not, I'm just telling you, if it is a very costly process, you would probably want to avoid it. So in those cases, I would consider all these variables, explicitly state them as X, and this one would be clubbed, or this one would go with the error part. Okay, do you see what I'm saying? So because I have limited resources with respect to time and cost, and I should collect data of the relevant variables given my constraints. Okay, so it is very good to have nice data of, you know, certain exotic variables or something like that. It would be very nice to have, but we mostly are restrained by cost and time. So we have to make the best out of whatever available resources we have, choose the relevant variables, and then proceed with data collection. Now once we have the data, so if you remember the data collection, we can collect data like first hand, that would mean primary data. We could also use someone else's data, and that would be secondary data. Okay, we learnt about this in the first few classes. Now once we have the data collected, then we need to specify the model, or in other words, we need to provide a guess, or we need to provide a guess structure of F. Okay, so we are going to assume that F is of the form beta naught plus beta 1 x and so on and so forth, and then proceed further to see how well this sort of a model is explaining whatever observed data I have. Okay, sorry. So once I have some assumption of the model, the next goal would be to fit the data as per assumption. So we have assumed that F would have a certain kind of a functional form. We are also careful, and we also know that even if we have all our x's, there could be some unknown sources of variation, which I am taking into account by inserting a random term called epsilon. And then now comes the point of fitting, which means that I have to get the estimates of the unknown parameters. Okay, so fitting the model as per assumption with data, this is something that we need to do. This would give us the estimates of the regression coefficients, and then once we have those, we will also have some predicted value of y given all these x's. Okay, so now once we have fitted the model, it's not like that we leave the entire problem and just carry on with our lives. We go back and then we critique the model and we also use model validation. So whatever we have fit, so is it good enough? This is something that we are trying to address with the help of model validation and criticism. Okay, so then once we have criticized the model, we know what is good or what works, what doesn't work, then comes the process of refining the model if needed. Okay, based on the results of the model validation, and then this would be the chosen model, and that would finally be used for prediction or forecasting. Okay, so with the help of, if I'm able to map the relationship between my dependent and independent variables on, I should be able to tell you as a statistician that how much do I expect a certain yield to be if I have this much amount of rainfall, this much amount of fertilizer, and so on and so forth. So my so there are two main goals in fitting a linear model. The first goal is that to understand the relationship. Okay, so goal 1 is to understand relationship between x and y, and once we have understood what is the relationship, then the goal is to use x to predict y. So these are like the two major goals of regression analysis. Mostly, we are interested in understanding the relationship, and once we know what the relationship is, we would want to go ahead and predict what the value of my y variable could be if I had a certain number of or certain values of my x variable. Okay, so this also helps in forecasting or prediction. So this was like a generic overview of linear models. Now if I want to move into the specifics, I should be talking about a simple linear model versus a multiple linear model. So simple linear regression model and versus this multiple linear regression model. So simple means only one independent variable, which means 1x, and multiple linear regression means multiple x's. So whatever examples I gave you in the previous slides, those were actually multiple linear regression models. And simple linear regression model is like a special case of multiple linear regression model. So we were talking about independent and one versus multiple independent variables. So if we have one independent variable, then we say that it's a simple linear model, and if we have multiple linear independent variables, then we say it's a multiple linear regression model. Now if we consider a model like this is actually a simple linear regression model, okay, where beta naught is actually what we called as an intercept and beta 1 is actually the slope. So if you remember y equal to mx plus c is actually beta naught and c is actually beta naught, yes, and m is actually b1. So it would essentially mean this line where this part is beta naught and the slope is beta 1, okay. So the slope of this line is actually beta 1. All right. Now whenever I am given, let's say, two variables x and y, let's say 1 2 3 4 5 6 something 10, and here I have 10 crop yields, okay. So let's say 42 some unit, 44, 35, 33, 25, 27, 47 something and so on. So whenever I have x and y given, my first instinct would be to plot x versus y and get a scatter plot, okay. So if I have a scatter plot like this, by seeing this I have this intuition that okay, perhaps as x increases, y also increases, okay. If I have something like this x and y where it looks something like this, then my intuition would be perhaps y decreases as x increases, okay. So maybe their relationship is like inverse, okay. So first and foremost thing when we have two variables is to plot a scatter plot and then check, okay. Now here let's say we fit a line y equal to mx plus c or y equal to beta naught plus beta 1, something like this. So let me fit this as my fitted line. Sorry, let this be the fitted line. Okay, now if you check these differences between the observed point and my fitted data is actually what? This is actually representative of the errors I am making in fitting the model. Correct? So what I am essentially doing over here is that had I been able to fit a line such that these vertical distances were as small as possible, then I would have had the perfect scenario. But even after fitting, I am seeing certain difference between the true y and my fitted y. Okay, so this actually, these yellow lines are quantifying the errors in fitting. Okay, and how we are going to fit this line is that we are going to fit this line in such a way that these errors are minimized, in the sense that the sum of squares of these errors are as low as possible. Okay, so in order to fit a linear regression, we make a certain assumptions. Now we'll write those assumptions here. So while fitting the model, we have something like beta naught plus beta 1 x1 plus epsilon. We assume that expectation of epsilon is 0. Okay, and we assume also that variance of epsilon is sigma square. Okay, we also assume that x is like fixed or non-stochastic, in the sense that x is not a random variable. Okay, but y is a random variable. So these are like the primary assumptions while fitting a linear model. Okay, now how are we going to fit the model? So estimation of parameters can be done in two ways. Okay, so first process is the process of least squares, and second process is the process of maximum likelihood. Okay, now least squares doesn't require any sort of distributional assumption, but maximum likelihood requires a distributional assumption. Okay, so let us learn about least squares. So the basic idea in least squares is we have these x's and these y's, and if this is the scatter plot that we have, and if this is the line that we try to plot, we can plot this, we can plot this, we can plot this. So out of them we are going to choose that point, that we are going to find a line such that these distances from the actual observed y and the line is minimized. Okay, vertical distances between observed y and estimated y is minimized. Okay, so this observed y is actually my y's. Okay, so let's say this is my y value, and this one here in this line, this is actually y hat. Okay, now I have to choose that line such that this orange distances are minimized as much as possible. Okay, so what do we do? These yellow distances are actually called residuals. Okay, and they are like quantifying the error term. Okay, so if I write it here, so y is actually alpha beta naught plus beta 1 x1 plus epsilon, and y hat is beta naught hat plus beta 1 hat x1. So y minus y hat is actually in some way giving me the difference due to error. Okay, and my goal here actually is to minimize this quantity yi minus beta naught minus beta 1 xi whole square I equal to 1 to n. If I have x1 y1 to xn yn, that is n data points. Okay, so goal is actually to minimize this quantity. Okay, and how do we do that? If we call this as S equal to summation yi minus beta naught minus beta 1 x1 or xi whole square I equal to 1 to n, we just derive with partial derivatives with respect to 0, with respect to beta 1 and beta naught, equate it to 0, then we'll have two simultaneous equations. We solve and we get the values. Okay, so what we essentially get is actually this thing. So beta naught hat becomes y bar minus beta 1 hat x bar, and beta 1 hat becomes Sxy by Sxx, where Sxy equal to summation xi minus x bar yi minus y bar, and Sxx is summation xi minus x bar whole square, I equal to 1 to n, I equal to 1 to n. Okay, and x bar is actually 1 by n summation I equal to 1 to n xi, and y bar is the same thing with yi. Okay, so once we have beta naught and beta 1, we can derive the Hessian matrix, which is nothing but the matrix of second order partial derivatives. So here we would have d2s b naught b1 by del b naught square. Here we would have d2s b naught b1 by del beta naught beta 1 del beta 1. So this is like second order partial derivatives. Here we would have del square s by del beta 1 del beta naught, and here we would have del square s by del beta 1 square. Okay, and we see that the determinant of the matrix is greater than equal to 0, and hence we say that beta naught hat and beta 1 hat are the global minimum, which translates to saying that if beta naught equal to beta naught hat and beta 1 equal to beta 1 hat, then the error, the sum of squares due to errors will be minimized. Okay, so once we know what and how beta naught and beta 1 is derived, we should be able to interpret what it means. So interpreting beta naught and beta 1. Now as I was saying, let's say I have something like this, y equal to beta naught plus beta 1 x1 plus epsilon. Okay, now if I have made the assumption, so expectation of y should be beta naught plus beta 1 x1. Now mind you, x is a non-stochastic term, so expectation of x1 doesn't really matter. X is actually a constant, you can call it a constant. So now if this is the fitted model, if x1 equal to 0, we will have expectation of y equal to beta naught. So what does beta naught actually mean? Beta naught means average value of y when x equal to 0. Okay, and again expectation of y equal to beta naught hat plus equal to beta naught plus beta 1 x, and if I write this like this, that if I consider x plus 1, so here I would have y star equals to beta naught plus beta 1 x plus 1. Okay, so if I do 2 minus 1, then I have beta 1 equal to expectation of y star minus y. So if I like to give it x equal to x plus 1, something like this. So what does beta 1 mean? Beta 1 means average change in y for 1 unit increase in x. So this is actually nothing but the slope. Okay, and if you want to call it differentially, so expectation of y equal to beta naught plus beta 1x. So del x expectation of, or I shouldn't write del, d dx of expectation of y is actually beta 1. So which also says that rate of change of x, so this is rate of change of average y for unit change in x. Okay, so if beta 1 is greater than 0, so we'll see that there is a change in the positive direction. We'll see scatter plots like this, and if beta less than 0, we are going to see scatter plots like this. Okay, right. Now that we have these interpretations and everything, let us move on to see how we can use the R software to solve these problems. Now mind you, this linear model can also be extended to multiple linear regressions, in the sense that here you would have certain other variables, and then this will become a little bit more complicated, not that much, but you would also end up having estimates like beta naught hat, beta 1 hat, and so on, and then the interpretation part will change a little bit. Okay, but we'll come to that later. First, let us find out how we can use the R software. Okay, so let's say I have I'm going to use the empty cars data set to demonstrate my okay, so this is the empty cars data set. If I press on F1 over here, I will be able to see what are the cars and what is the data frame with the number of observations and number of numeric vehicles. Like, this is what the data actually looks like. Okay, in total we have n equal to 32, so here n equal to 32, so we have 32 observations on 11 numeric variables. And what are these? Like miles, number of cylinders, displacement, something related to cars. Okay, and it is presumed that miles per gallon is, let's say, dependent on these other variables. Now for the time being, I am going to use x as weight and mpg as y. So let me assign that y equal to empty cars dollar mpg. This is my dependent variable. Okay, this is n, that is number of data points, and this is my data set empty cars. Let me save it in an appropriate folder. Yeah. Okay, so y is my dependent variable, and as my independent variable I am choosing x as weight. So empty cars dollar weight. Okay, so let me first get a scatter plot of y versus x. So how do I do that? I just do a plot x comma y. Now we see that as we move away, like as x increases, y decreases. So here we see an inverse relation, that is as weight increases, miles per gallon decrease, and this looks like an expected behavior. Okay, I could use labels like x lab equal to weight and y lab equal to miles per gallon. Okay, and let me add a title as well. So main equal to scatter plot, let's say. Okay, now that we see an inverse relation, and this looks like a straight line, like I could fit a straight line for this data. I could also fit a quadratic, but let me first fit a straight line. So in order to do that, I am going to use this command lm y on x. Okay, and once I just run this thing, it is going to give me the estimates of beta naught. So from here I have b naught. Instead of calling it beta naught, I am calling it b naught. B naught equal to 37 point this thing. This is what I have. And b1, that is slope, is this thing minus 5.334. So here we see that b1 slope is less than 0. So we have this negative relationship. All right. Now, if this is how my model is fit, then how do I interpret these things? So it means that if weight of a car, or I should say if a car is weightless, even then the miles per gallon would be 37.285. Okay, and here B1 means that whatever the unit is, I forgot what the unit is, so let me see what the unit of weight is. Weight is 1000 lbs. Okay, so here we'll interpret it like this, that increasing weight by 1000 lbs decreases mpg by 5 point decreases mpg on an average by 5.34. Okay, so this is how we should be interpreting the regression coefficients. Now that we have these regression coefficients, let us try to fit this line and see how well does it fit the data. So I'll call this as model, this LM, and if I give a plot abline model and color equal to red, after this thing, oh wow, need finite x-lim values. What is wrong here? Okay, and y is again this. Okay, let me just draw y predicted. So if I want to do fitted, I should give predict model. Then this is actually how my fitted curves looks like. Okay, this one I'm not so sure why it's not working. Need x-lim values. Let's find out. They are saying that it could be possible that there is an NA value, but I don't see an NA. Let's check. Is dot NA x, all are false. Is dot NA that is also false. So perhaps I should clear this environment and then run it. Why is it giving this? Okay, so this is actually fitted is actually giving me the fitted line, and I should be having, I don't know why I'm not getting this, what the error is. No non-missing arguments to mean. So if I give minimum of x and then maximum of x, minimum of y and then maximum of y, yeah, everything seems to be in range. God knows why this is not working. Okay, I should not give plot, I should only give abline. That was my mistake, because plot requires two arguments, x and y. Okay, right. So this one, abline x and fitted, or I should only write abline model. Yes, so this is how the regression fits the data. Okay, and the vertical distances are the departure of the observed y from the predicted line. Okay, now we also know how to get y pred, or the fitted value, or y hat. So fitted equal to predict model. Okay, now let's say if I have a new set of prediction. Okay, so if I have x new equal to, let me just randomly generate. So if I generate, let's say r unif, randomly I'm generating 32 samples, mean equal to 32, max equal to 42. Okay, so x new, I have these many samples. Let me set a seed so that it is easier to replicate. Okay, so x new is this thing, and now if I want to have the new predictions, new pred, all I need to do is I need to give predict model, and then x and data I need to give or x I need to give as x new. Okay, so new predictions would be for this new set of x's is this thing. Okay. Let me just see this predict function once again. Yep. Okay. So if I give data or new data equal to x new. Okay, so new data, if I do data dot frame x new, yes. So this is how the new predictions would look like, and this is how the fitted okay, so this is how the fitted model would look like. And then if we want to get the residuals, we should write resid and then model. This is actually giving us the residuals of the model. Okay. Alright, so this is how the residuals would look like. Now once we know how everything looks like, we can also plot residuals versus x. So if I do a plot residuals versus x, and then residuals, and we see that these points are scattered about 0 randomly, then this is like one way of validation that perhaps model fit is okay. Another thing that we can see is by using summary of model. Okay, so if we give summary, we are going to get something like this. okay, where here we would have the estimates beta hat and beta naught hat and beta 1 hat, their corresponding standard errors, and this part t and p value, these will come later when we talk about testing, okay. And this one here, multiple r square, is actually telling me how much proportion of variance in y is being explained by my x, and which is like a considerable portion. And overall I can see that these are randomly scattered and the p value is quite small, so perhaps this is a good model. Alright, so this is how you would carry out a regression analysis and then proceed to test for model validity. There are several other methods. This is like one fundamental basic method that I'm telling you. And then we would look at some other aspects of like updating the model that we were talking about, but those would come mostly in the context of multiple linear regression. For simple linear regression, this is like the basic workflow. You have the data set, you have the number of data points, the dependent and the independent variable, the scatter plot, and you see that there exists some sort of relationship. You try to fit a line, you try to fit a curve or something like that, but mind you, that should be linear in parameters. And then once we have that, we get the regression coefficients, we get the fitted values, we get the residuals, we plot residuals against x if it is a simple linear regression, and then we see if it is randomly scattered about 0 or not. If so, well and good, our model works well. Okay, yeah, so on an average the residual sum should be 0, right? Okay, so this was all about regression analysis. I hope this was helpful, and if there are any doubts, please reach out and post in the discussion forum. Hopefully we'll be able to help you. Thank you so much for joining, and I'll see you in the next class. Bye bye.